Hello everyone, and welcome back to another tutorial video. In this video, I will be tackling some problems from homework set number 5 that covered the solutions, or finding general solutions, of second-order linear homogeneous equations. Alright, this should be a shorter video, I think, and the reason for that is that the main tool that we're going to be relying on in this video and in these problems is the theorem that I have now written up for you guys on the screen, called the principle of superposition. And it basically states that if you have a second-order linear homogeneous equation, and you've already found two solutions to that second-order linear homogeneous equation, then any linear combination just means that you can multiply each of those two solutions by any constant and then add them together. And whatever constants you choose, you'll still have a solution to the same equation. Now, we're going to use this tool in these exercises to be able to solve these equations in specific cases. But keep in mind, I really do want to reiterate something that I mentioned in class, which is to say that in practice, this doesn't come up quite as often as we'd like, if only because getting those two solutions to begin with is quite hard. And for that reason, in most of these problems, the first step that you're going to be asked to perform, at least on the homework sets in the online homework system, asks you guys to actually check that two provided solutions do actually satisfy the equation. So I'm going to work through these problems entirely in the way that the homework set asks you guys to do them. Alright, let's put this up in the corner as usual for people to refer back to as the video goes along. Alright, here's the problem that I'm going to tackle in this video. It is exercise 3.1.3 from the textbook. This exercise gives us a second-order linear homogeneous equation, which is y double prime plus 25y is equal to 0. You can see it is homogeneous because the right-hand side is 0. And clearly this guy is linear because there's absolutely nothing fishy going along here. Now this is a two-part problem. In the first part, you are given the two equations, y1 is equal to cosine of 5x, and y2 is equal to sine of 5x. And you are asked to check that both y1 and y2 are solutions to this equation. Then, in the second part, once you've completed that, you are given that y of 0 is equal to 7 and y prime of 0 is equal to 3. And you are asked to find the particular solution to this differential equation. Now, for this problem, it is in that part 2 that we are going to rely on our principle of superposition theorem. In part 1, all that we are doing is taking derivatives, plugging in, and verifying that the equation is satisfied. So let's get right to it. Alright, I've made some space, and now let's check. So we need to check that y1 is equal to cosine of 5x works. Alright, given that our equation is second-order linear, we're going to need to compute both derivatives, or compute two derivatives. Then plug into the initial equation. Alright, y1 is equal to cosine of 5x. That means that y1 prime is going to be equal to, I believe, negative 5 sine of 5x. And therefore that means that y1 double prime is going to be equal to negative 25 cosine of 5x. Now if we plug in, we see that y double prime plus 25y is equal to negative 25 cosine of 5x plus 25 cosine of 5x, and this is indeed equal to 0. So the differential equation, which again, reminder was y double prime plus 25y is equal to 0, is satisfied. And that's all there is to it. We've checked this first solution, and it clearly works. It's really nothing complicated for this first part. There's really nothing fancy. You're just taking derivatives, plugging them into the differential equation, and just verifying that it gives you what it's supposed to give you. In this case, that's supposed to give us 0, and that's exactly what we got. All right, we're going to do the same thing with y2. y2 is sine of 5x. You can see that y2 prime will be equal to 5 cosine of 5x, and y2 double prime will therefore be equal to negative 25 sine of 5x. Now we're going to plug this in again, and we see that, oh, I forgot my y1s up here, I apologize. Here are y2 double prime plus 25 y2 is going to be equal to negative 25 sine of 5x plus 25 sine of 5x. And once again, this gives us 0. All right, you wouldn't really have to show much more work than this on the exam. This is very straightforward. Do at least write, give some idea of what it is that you are doing. At least mention that you're plugging in, and at least once write that just point out that the differential equation is satisfied. And then once you've done that once, you can just get by with just a check mark like I've done here, after you've checked each step or each given solution. So don't worry too much about that much work here, just as long as it's clear what you're doing and that you've ticked off all the boxes that you need to tick off. All right, that's all there was to the first part of this problem. We've double-checked that both y1 is equal to cosine of 5x and y2 is equal to sine of 5x are both solutions to that second-order linear homogeneous equation that work. All right, now as I mentioned, up until now we have not had to use this theorem of superposition. Now is when it's going to come into play. Because we've completed step 1, we're now going to have to do the second part of this problem, which is giving us that y of 0. Let's actually make a little box here. So we are now given that y of 0 is equal to, I believe, 7, and y prime of 0 is equal to 3. Recall that because this is a second order differential equation, we need 2 initial conditions to be able to get a unique particular solution. All right, now we are given these 2 initial conditions, and you are asked to find the particular solution of the differential equation that satisfies these 2 initial conditions. Now, as I mentioned in class, in general, this would be a very hard thing to do. However, in this case, we already have y1 and y2, which work as solutions of the general equation here. And so we're going to use our principle of superposition to be able to solve this, because we have this head start, if you would. All right, how do we do that? Well, we know by the theorem of superposition that y is equal to c1 y1 plus c2 y2 is a solution. I.e., now we're just going to plug in what y1 and y2 are. Y is equal to c1 times cosine of 5x plus c2 times sine of 5x is a solution. So now what we need to do is basically just do exactly what you guys are used to when it comes to initial conditions like these. We are just going to plug in those initial conditions and see what we can solve for. So now we are going to plug in y of 0 is equal to 7. And if we do this, we see that we have 7 on the left-hand side is equal to c1 times cosine of 0, because 5 times 0 is 0, plus c2 times sine of 0. Now you may recall from trigonometry that cosine of 0, this guy, is equal to 1. And that sine of 0 is equal to 0. So in other words, this guy actually simplifies quite a bit, and we get that 7 is equal to c1. So in other words, we have that y is equal to 7 cosine of 5x plus c2 sine of 5x. We are almost there. We now need to use that second initial condition that's given, but that initial condition is given with respect to the derivative. So we need to plug in that y prime of 0 is equal to 3. Now in order to plug this in, we need to take the derivative of this guy. So doing that gives us that y prime is equal to 7, the derivative of 7 cosine of 5x is going to be negative, I believe, 35 sine of 5x. And then the derivative of c2 sine of 5x should be 5 times c2 times cosine of 5x. All right, now we plug in the fact that y prime at 0 is equal to 3. So y prime is 3. Then we have, this is equal to negative 35 sine of 0, because 5 times 0 is 0, plus 5 times c2 times cosine of 0, because 5 times 0 is 0. And once again, keep in mind that sine of 0 is 0, and cosine of 0 is 1. So this gives us that 3 is equal to 5 times c2. So therefore c2 is equal to 3/5. All right. So at this point, we are actually just done, and you can see how helpful this was. All that's left for us to do is simply to rewrite the full solution. Let's see if I can make a little bit of space here. All right, I've made just enough space to write the very final line. So we get the solution, or the particular solution, where we've found that C1 is equal to 7 and C2 is equal to 3/5. So therefore we have the particular solution. Y is equal to 7 cosine of 5x plus 3/5 sine of 5x. And we are all done with this problem. So like I said, this is a shorter video because this is actually pretty straightforward. In fact, if you want, you can actually double check, just like we did in part 1 with y1 and y2. You can double check that this particular solution does in fact work as a solution to the equation y double prime plus 25y is equal to 0. And furthermore, you can plug in x is equal to 0 into this equation and into the derivative of this equation. And you will see that at 0, y will be equal to 7, and at 0, y prime will be equal to 3, just as desired. So once again, this sort of, what's the idea here? What have we done? The long story short is that we lucked out in this case. We were given a very specific type of equation, which was second order, linear, and homogeneous. Not only that, but we lucked out into having not one, but 2 working solutions for it already just from the get-go. We were just given those. We knew what those 2 solutions were. We didn't have to put any effort into finding those solutions. We just knew that cosine of 5x and sine of 5x both worked. And because we were this lucky, we were able to use this principle of superposition to basically find any other solution or any particular solution that was needed to this differential equation. This is very cool, but I do always want to emphasize the extent to which this only really works in specific contexts, and you really do have to get lucky with getting those 2 solutions to begin with. If you don't have them, then this principle of superposition is not going to help you at all. Alright, that's all I have for this problem, but I do want to leave you guys with just I guess, 1 or 2 comments on, I believe, the last question that I put on homework number 5. So in that very last question, I want to clarify that what's going on there is that you are being given an equation, a differential equation, which is actually very specifically not linear. And what you're asked to show is that this principle of superposition, the one that I've written in the top left of the screen here, does not apply whenever you're no longer in a linear differential equation context. So that, I just wanted to clarify that that's the idea going on in the very last problem on this homework set. I'm not going to do a tutorial on that, I don't think, but I did want to mention what the idea is there, because I think that's a useful problem to illustrate how specific the context needs to be for us to be able to do the type of thing that we've just done in this video. Alright, that's all I had to say for this. As usual, if you have any extra questions or other topics you would like me to cover, please let me know by email. And otherwise, I will see you guys in class. Alright, bye-bye.